Hello viewers and fellow math students revising for EOI. Welcome. Today, this video will be going through about 3 different types of logarithm questions. Let's dive in. So, we have the first question here. Given the equation log base p of x plus 8 minus half log base square root p of x minus 4 equals 2020 to the power of log base 2020 of 3 suggests a pair of values for p and x. How do we do this question? So firstly, must write the equation out again, as this will be part of our presentation. Next, we can see that 2020 to the power of log base 2020 of 3 will equal to 3. So we can write that down. Next, we can move the half to the x minus 4 inside the logarithm. So the logarithm will be log base of square root p and it will be x minus 4 to the power of half will give us 3. Next, we want to convert both logs to the same base. So we have log base p of x plus 8 minus, we have to convert this logarithm to a base of p. So we need a fraction. So we got log base p of x minus 4 to the power of half, and the bottom will be log base p of square root p, and this will give us 3. Next, we can see that this bottom part, log base p of square root p, is equals to half. So we can write log of p base p of x plus 8 minus, you can also see that the numerator of this has a power of half. That means we can write the half in front over here. We can have log p of x minus 4, and underneath is half. And this will give us 3. As you can see, the numerator and the denominator have a common factor, which is half. So you can remove the half. So we have log base p of x plus 8 minus log base p of x minus 4 will give us 3. Next, we can combine both logarithms into one single logarithm with log base p of, so to combine two logarithms where one logarithm is subtracting the other, you must divide what's inside the logarithm. You have to divide x plus 8 by x minus 4. So we got this x plus 8 over x minus 4, and this will give us 3. Now we want to swap this logarithmic form into an exponential form, which means we have to start with p to the power of 3 equals to this whole fraction over here, it's x plus 8 over x minus 4. So this is the equation you're going to use to solve this question. So this question says suggest a pair of values for p and x. That means we can come up with a value for either p or a value for x. And there is no standard value for p and x. So what we're gonna do now is we can let p be any number of your choice, but in this question I picked 2. So 2 to the power of 3 equals fraction x plus 8 over x minus 4. So we've got x plus 8, we multiply x minus 4 on both sides, so x plus 8 equals 2 to the power of 3 is 8, so 8 and x minus 4. So we have an equation where there's only one variable which is x. So x plus 8 equals 8x minus 32. So x 7x if you minus x on both sides and add 32 on both sides, so you got 7x equals 40, and this gives us x equals 40 over 7. Okay, how about if we let p be another number? Let's say let p be 4. So we sub p into this equation. So 4 to the power of 3 equals x plus 8 over x minus 4. So we've got a repeat of this situation over here. So we've got x plus 8 equals 4 to the power of 3 is 64. 64 times x minus 4. So x plus 8 equals 64x minus 256. So we can find what 63x in this case, if we minus x from both sides. 63x equals, and then we add 256 on both sides. So 63x equals 264. So x equals to 264 over 63. Which gives us 88 over 21. So we are simplifying the fraction here. You do not need to do all of these steps during the exam, and as long as you have one pair of values for p and x, you are just good to go. So this equation is what makes you win this question, like what makes you get this question correct. So our final answer is one pair of values. See, one pair of values for p and x is p equals to 2 and x equals to 40 over 7. Right, done. Full stop. And we have solved question 1. Just a reminder, you do not need to do this during the exam, but if you want to check your answer and check your working, you can always do this additional step. Now, let's dive into question 2. So question 2 says, use the substitution u equals 2 to the power of x to express the equation, this equation. So hence, solve this equation. So, how do we solve this question? As you can see, this question is also a function question and logarithm, specifically exponents question. So, okay, let's move this question down. So, let's start by copying this equation out. So, this substitution here is meant to help you to easily solve this equation easier. So we must simplify this equation so that only 2 to the power of x is left. So first step, we must simplify 2 to the power of 3x plus 1. So we've got 2 to the power of 3x times 2 to the power of 1, which is just 2, plus 7, 2 to the power of x. There's no need to change this 7 times 2 to the power of x, because we can easily substitute it to u later, equals 4 minus 2 to the power of 2, bracket this up, and to the power of x. You see, 4 equals 2 to the power of 2, and we got an exponent x here. So we've got 2 to the power of 3x, which is the same logic for this one. So we got 2 to the power of x. Can rearrange this. 2 to the power of x to the power of 3 times 2 plus 7 to the power times 2 to the power of x equals 4 minus 2 to the power of x to the power of 2. You'll see why I do not simplify this to 2 to the power of 2x later. So we have our 2x's ready. Got 2x, 2x, 2x. So you can substitute sub u equals to 2 to the power of x into, let's say this is equation number 1, into equation number 1. So this is why I do not simplify this into 2 to the power of 2x, so I can substitute u in easier. So we've got 2x to the power of 3, which is u to the power of 3, times 2 is 2u to the power of 3, plus this is 7, and this is 2 to the power of x, so this will be 7u, equals 4 minus, you see, this is 2 to the power of x is u, so 2 to the power of x to the power of 2 is u to the power of 2. So you just make this into a cubic equation with one side being 0. So 2u to the power of 3 plus 7u equals, plus u square minus 4 equals to 0. So now we need to find what is u. So firstly, let's let f function of u. See, here comes the function part. Function of u equals this whole equation, but without the 0. So we need to try. Again, you can use your calculator to find the solutions for u. I've did that before, and u equals half is one of the solutions. So try u equals half. So f function of half equals 2 times half to the power of 3 plus half to the power of 2 plus 7 times half minus 4, and this will give us 0. So using factor theorem, u minus half is a factor. So you can use long division or syntactic division or any division. So you must use long division function of u divide by u minus half equals this whole thing divide by this whole thing at the bottom, and this will give us 2u to the power of 2 plus 2u plus 8. So we've got this factor, this linear polynomial times this this linear expression times this quadratic polynomial equals to f of u. So we can now solve it. So u minus half two u to the power of 2 minus a plus 2u plus 8 equals 0. So u minus half equals 0, or 2u to the power of 2 plus 2u plus 8 equals 0. So this is easy. This first part is easy. U equals half. So, and this part, so you can see, you can observe that this quadratic equation has no real solution because discriminant, which is b squared minus 4ac, b in this case is 2 squared minus 4 times 2, which is a, times c, which is 8. And this gives us negative 36. Negative 36, which is lesser than 0. Therefore, u equals half is the only real solution, and we need to write here that there is there is no real solution for 2u to the power of 2 plus 2u plus 8. Let's just put since there is no real solution. So we've got 2, so we need to sub back u equals 2x to the power of x, so 2 to the power of x to the power of x equals half. So we need to use logarithm here. So log base 2 of 2 to the power of x equals log 2 of half. So you can see the left side simplifies to just x equals, and the right side simplifies to -1. So we have solved this question, x equals -1. Now let's move on to question 3, which is a rephrased question. We'll be looking into Moore's law. So Dr. Gordon Moore, co-founder of Intel, speculated in 1965 that the number of transistors in an integrated circuit would double at the end of every 2 years. His speculation, now known as Moore's law, can be expressed as n equals n0 bracket 2 to the power of 0.5t close bracket, where n is the number of transistors, t is the number of years after 1965, and n0 is a constant. In 1965, a silicon chip contained 240 transistors. Find the value of n0. So, how do we do this question? We have n, which is 240 transistors, and we have t, which is the number of years after 1965, which is 0 years, because this year in this question is 1965, and t represents the number of years after 1965. That means we can go sub t equals 0 and n equals 240. So 240 equals n 0 square bracket 2 to the power of 0.5 times 0 close bracket. So we can find n0. So n0 equals to 240 over 2 to the power of 0.5 times 0. And if we key this into a calculator, it will become 240. That'll be our answer for number 1. Okay, next question II. Here's where the tricky part comes in. So we need to find the year in which the number of transistors will exceed 1 million. So how many zeros are in 1 million? So 1 million has 6 zeros. 1, 2, 3, 4, 5, 6. Close. So when number of transistors exceed 1 million, n is greater than 1 million, 1, 2, 3, 4, 5, 6. Sub n 0 equals 240 and n is greater than 1 million. So this will be an inequality with 240 times 2 to the power of 0.5 t equals, greater than, will be greater than 1 million. One, two, three, four, five, six. So we divide 240 on both sides. 2 to the power of 0.5 t is greater than 1 million 1, 2, 3, 4, 5, 6 over 240. So if we put a log base 2 on both sides, so log base 2 of 2 to the power 0.5 t is greater than log base 2 of this fraction. And we can see that 0.5 t is equals to this expression over here. So 0.5 t is greater than log base 2 1 million over 240, which is this big fraction over here. So we have to convert the base of the log to be either 10, base 10 or base e, because in our default calculator, the log is by default base 10 and ln is by default base e. So 0.5 t is greater than, so we have another fraction because we have to change the power. Log base 10 of this fraction over log of 2. If we use calculator, t will be greater than 2 times this whole chunk, which we can finally key into the calculator. So t is greater than 24.049. To 5 SF. So since here says it will double at the end of every 2 years, that means t must be a whole number. So since t must be a whole number, since as t represents years minimum of t equals 25, because the 25 is the smallest whole number, which is larger than 24.049. So therefore the year in which number of transistors will exceed 1 million equals 1965 plus 25, which gives this 1990. So part I. According to Moore's law, how many transistors would there be on an integrated circuit in 2025? Express your answer to the nearest billion. So, we can just go straight to the equation. So n equals, with n0 is 240 times, we need the square brackets here, 2 to the power of 0.5 times, since it says here the years, t is the number of years after 1965. That means we can't plug 2025 inside here. We need to plug 2025 minus 1965. So, square bracket. So n equals, if we key this into the calculator, it will show a very weird number, which is 2.576980,378 times 10 to the power of 11. So how do we find how many digits does this have? So if we look to the other side, if we look to the side which has the times 10 base on it, it shows there is times 10 to the power of 11. So this whole number has 11 digits. So if we write it out, it will be 257,698,0378 will be the first 9 digits. And since this question asks us to express our answer to the nearest billion, that means the last 2 digits is not really needed. So let's say our last 2 digits are zeros. So we'll have this very weird number, very weird and large number. So 25,76,98,037,00. So here's the comma split. 1 comma, 2 comma, 3, 4, 6, 7, 3 comma, wait, my apologies, there's another 0 over here, 3 comma, and 4 comma. So they're asking for the nearest billion, so we do not need the back part. We only need the first 4 digits, which is 257 and 6, which means we have to round this number up. To be 258 billion. So let's write our therefore statement. Therefore 258 billion transistors would be on an integrated circuit. In 2025. Done. So that's it for today. See you in the next one. Bye. So, how do we do part 3? Part 3 states that, according to Moore's law, how many transistors would there be on an integrated circuit in 2025? Express your answer to the nearest billion. So firstly, how do we solve this question? We can see that the year is given, so we can find what is t, and we already found n0, which is 240 transistors. So n equals 240 times 2 to the power of 0.5 times 2025 minus 1965. And this will give us a really weird number, a really weird and a really big number, which is 2.576980378 times 10 to the power of 11. So this shows that this answer has 12 digits, and here's a way to check it. So there's already 10 digits on the number that is given, other than the times 10 to the power of 11. And if you click answer divide by 10 once, and you click the equal sign twice again, it will give you an answer that is not with the times 10 to the power of something. So 25769800378 has 2 digits at the back. That means 8 is the 100th digit. So let's just say 257. I'll use commas for for easier understanding, but don't use commas in exam. 037, that's 8. And since we click the equal sign twice, must put 2 placeholders. So placeholders can be like anything. You can put x, xy, or you can just put 00. So this is our answer, but we need to round it off to the nearest billion. So we have this place is the billionth part. So we just need to see whether 6 is above 5. So we need to round this part off. So it becomes 258 billion to the nearest billion. So therefore 258 billion transistors would be on a circuit in 2025. That's it for today's video. See you in the next one. Goodbye.